Hello students, welcome to UPG Pathshala. I am Dr. Vail Pandian from All India Institute of Medical Sciences. Today I am going to talk to you about the module about working principles of HPLC and its applications, part 1. This is from the paper Techniques in Molecular Biophysics 1. So today's lecture I am going to talk to you about the basic construction of HPLC, working principle of HPLC, and how we characterize an HPLC chromatogram. Basically, this HPLC is derived from the chromatography technique, high performance liquid chromatography. The performance has increased from a simple liquid chromatography. So I hope that you remember a Russian botanist Sweat first demonstrated the separation of carotenoids in a column. Thereby the name chromatography derived. Chroma means color, graphy, the technique through which its separation happens based upon color. So it's chromatography. Where we are using liquid, therefore is a liquid chromatography. So sometimes instead of liquid we use gas, therefore it is derived as a gas chromatography. There are some fundamental rules through which the separation happens. Today, separation science has become a very big area in which these HPLCs are commercialized, and apart from a normal high performance liquid chromatography, today we got ultra high performance liquid chromatography where a conventional pressure which is tolerated by HPLC has tremendously increased. And we thought earlier, we thought that we won't be able to go above the dimensions of normal HPLC. Today we have gone further and we could get inside a much more finer separation than one could think of. So today let me just explain you more about the HPLC. In HPLC, different types of HPLC are being used. When we try to categorize them for our understanding, I would say HPLC itself can be defined as high performance, high pressure, or highly priced. Anyone will fit for this P, high performance liquid chromatography or high pressure liquid chromatography or a highly priced liquid chromatography. But when you just get inside the machine, we need to understand that the separation happens in the chromatography is based upon few fundamental rules. It could be adsorption, could be partition. Sometimes the principle is by size exclusion or ion exchange. HPLC is an instrument which is used to separate and quantify the compounds from its mixture. By and large, when we try to differentiate the types of HPLC, the methods employed in HPLC, you divide this into two types basically, that is isochromatic and gradient. Isochromatic means the solvents which are used in HPLC are always kept in same proportion and they are not changing. But the solvents, they change mutually, then along with time it is called a gradient. The HPLC, based upon the nature of the compound, slowly it gets eluted from the column and it is getting detected in the suitable detector. Basically, HPLC contains two fundamental things. One is mobile phase, another one is stationary phase. The stationary phase here is the column and the mobile phase is the solvent which is used to elute the molecule is the mobile phase. Now based upon the application, for our convenience we try to classify them into different ways. When you just look into it, a normal phase, when the HPLC developed, people prefer to use normal phase. That means polar stationary phase and non-polar mobile phase. Silica was first compound which was used in this HPLC columns for separation, in which an organic solvents like ethyl acetate or benzene, chloroform, tetrahydrofuran, all these things are used, non-polar solvents are used for the separation. That is why it is called a normal phase. What is normal about it? The silica is hydrophilic, upon which hydrophobic solvent was used. Then came reverse phase. What we have done, we converted the stationary phase as hydrophobic, upon which hydrophilic solvents are used. The hydrophilic solvents are water-based solvents. I mean, they are miscible in water and any ratios. Water, methanol, acetonitrile are used in most of the applications in reverse phase chromatography. The stationary phases are predominantly silica-based but surface modified with non-polar carbon chains like C8 carbon chain or C18 carbon chain. Sometimes the surface modified with phenyl ring, so that you get different types of column chemistry. Ion exchange chromatography, in which the stationary phase is would be having a resin, and that is, it could be sometime cationic resin or anionic resin, based upon which the mobile phase would be changed from mobile phase would be using aqueous solvents, which will be having different ionic compositions for its solution. Next comes size exclusion. Of course, the size exclusion won't come under the high pressure liquid chromatography. This classically comes under low pressure liquid chromatography, in which predominantly the gel, silica gel, is used with the pores, larger pores, which is used for the separation of larger proteins and polymers. These kind of columns are used for isolation of antibodies, isolation and purification of particular peptide, immunoglobulins. For all these purposes, size exclusion chromatography is much used. Let me try to show you the basic parts of the HPLC in this simple representation. What you see here is a mobile phase reservoir, in which sometimes what you see here is an isocratic HPLC, in which water and methanol, water with acetonitrile or methanol alone are mixed together and kept it in the bottle, and it is being degassed. Sometimes the primitive HPLC systems never came with inherent or along with the degasser, online degasser. So it's always important that we used to do the degassing in our laboratory, either by sonicating or by using filtration assembly to remove the dissolved air as much as possible. Then you try to pump it through with the help of a pump. It is constantly allowed to flow in a rate which is specified, usually 1 ml per minute or 2 ml per minute or 0.5 ml per minute, depends upon the column. The column in the pump never produces any pressure. It works only for the flow rate, but the pressure is exerted by the column depends upon the particle size of the stationary phase. If the particle size decreases, the surface area increases and the pressure increases, back pressure increases. In between the column and the pump, injection port is kept. Usually in most of the HPLCs today, almost 99% of the HPLCs use a rheodine injector. Is a very nice, good technology through which, without disturbing the flow, you can inject the sample. Once the sample is loaded, it just applied on the analytical column, where the mobile phase is continuously eluting on the column. So slowly the separation happens. The compound which is having higher affinity towards the stationary phase stays more time in the column. The one which is having a low affinity for the stationary phase elutes. So in a typical C18 column, when you try to run benzene and acetone, acetone run comes first, and then comes benzene. For a mobile phase with 1:1 acetonitrile water or methanol water. So when it comes out, they should be able to identify by using a detector. The question comes up, what is the nature of the compound? If the compound is having UV absorption, you may like to use a UV detector to know continuously. You want to monitor for the presence of any analyte coming inside by using UV detector of a particular wavelength. Or if you are using a fluorescent detector, you will be dialing it for a particular emission and excitation and emission to get a particular fluorescence. And if you are trying to, if a compound doesn't have any one of this kind of character, or if a contact is sort of a sugar, and you might like to use a refractory detector in which the refractory changes are monitored, and all these signals which are being generated in the detector is getting converted into an electrical signal. Either it is integrated by using a integrated, or by using a software, this is getting converted into a visual display, and as a result the eluting compound creates a peak in the output device, and based upon the height of the peak or the area of the peak, the calculation is done for various grades of or various concentrations of a standard. From this calibration curve you try to understand an unknown compound, a concentration of an unknown compound, concentration of a substance which you want to quantify. What you see here is the modular HPLC, which is completely integrated one. This is having three components, distinct three components that are lined up in series. The lowermost one is the pump, which is shown there inside, where the solvents which are coming from the top are being pumped by the reciprocating pump in a particular pressure. This HPLC is coming under the classification of ultra high performance liquid chromatography. Here the pressure which is capable of withstanding the pressure up to 15,000 pounds per square inch, which is multiple times higher than that of a normal HPLC, but this can handle the column which is having a particle size of 1.5 micrometer also. So before this you have online degasser, membrane degasser. It tries to remove the soluble air in the solvent, thereby you don't have a chance of making bubbles inside the detector cell. So it is also coupled with the autosampler one, and the pumped solvent goes to the next compartment just above. Here what is shown there is the membrane degasser. The membrane degasser, as I told you, that it removes the air. Then from here the solvent is being pumped towards the next compartment, that is just right above this pumping station. The solvent is getting transferred, but before it is getting into the column, it goes through injector port, and the injector is an auto injector here. Therefore, to make the auto injection possible, so what you see here is the compartment which is for column and injector, and here is a sampling port, is having a robotic arm through which the sample is being picked up from the 96 well plates and being by the syringe, and it is loaded into that rheodine injector, and the injector is pneumatically controlled, and it works once you get the trigger, it opens it up, and while opening it, it feeds the sample inside the column. And when the column what you see here is a small one, that the whole compartment is thermojacketed, so you can keep the temperature constant for working at it. It enables us to work with the higher temperatures also, where it requires the setting of temperature at higher digits, about 40 degrees centigrade or 45 degrees centigrade is possible. And after leaving the column, it reaches into the detector. Here the detector is a photodiode array detector, and this detector is continuously monitoring for all the available nanometers. It's from 190 nanometer to 700 nanometer. Now it is set for a particular range, and from there the element goes into the mass analyzer as a sample feeder. So here the HPLC working as a sample feeder for the mass analyzer, where this goes and fed into the ESI mass. Or you see above are the reagent bottles. This is a quaternary pump, basically capable of handling four of the solvents together. It enables us to go for isocratic as well as gradient run in different run rates, right from if we go as less as 0.1 ml per minute, we go even less than 0.1 minute to 2 ml per minute is possible to reach with this. And right now it is going to the drain, but when it is required, we connect it with this assembly so that it is fed into the mass analyzer for direct analysis of the eluent which is coming inside. It gives both UV data as well as mass data. The signal which is obtained from HPLC is being processed by the software. What you see here is the ultraviolet spectrum at a particular wavelength. What is it? There are two peaks what you are able to see at a particular wavelength of 270, but you are getting a two separated, well separated peaks what you are able to see. But whereas this shows only one particular wavelength. However, you will be able to see more information about other peaks by using another option, that is, as we are using a photodiode array detector. Here I am trying to show you both the application of both single channel UV detector as well as the purpose of PDA detector. See here, look, you get a three-dimensional view of the structures. Here, completely in one dimension you are having time in minutes, and another axis you are having nanometers, that is UV nanometers from 200 to 400 nanometers, and in the y-axis you are having absorbance in milli-absorption units. Together, this gives a three-dimensional view of the peaks we are getting emerged out of this. This chromatogram shows the separation in the UV in single channel. Let me explain you column separation methods, which if you just get inside a column, what you see over there. In a bonded silica column, what you see here is the stationary phase. You see here typically a column in which usually it is made up of a stainless steel to withstand very high pressure. It is packed with silica or with a modified material which is having sort of end fittings through which filters are kept in both sides, and the solvent is allowed to pass through it in a standard column, in which if we just get inside further, you see a different beads of silica having a different particle size. In a standard analytical column, about 5 micron particle size is mostly used in analytical separations. Today, we have even 1.5 micron columns and 3.5 micron columns, and sometimes about 30 years back we have even used 10 micron particle size columns. So whenever the particle size goes small, you will get a lot of back pressure. So basically silica is easily available. It is chemically inert. It gives enough tensile strength, and it gives is a good matrix, and which fits into all criteria for a material to be used as a stationary phase, as it is non-reactive. And salinol groups gives another advantage for chemical derivatization into different polarities. For example, if you attach a C18 as you see in the picture, the silica paxin, when you try to derivatize it with the C18 chain, it gets converted to a C18 column. That is a normal phase which is having a salinol group as a hydrophilic salinol group is getting converted into a hydrophobic C18 chain, which is highly hydrophobic. Now, when you are passing a solvent through this, hydrophobic solvent like acetonitrile or methanol, they try to adhere to this C18, and thereby you are trying to create a sort of a partition between two liquids. This partition is making partition chromatography effective when you're using two solvents together, especially water and acetonitrile or water and methanol, etc. Sometimes we use directly only one solvent, that is methanol. When you use methanol, it behaves as an adsorption chromatography. When you use two solvents, it behaves like a partition chromatography. That is how the columns they are behaving in the HPLC, which allows you to separate the compound. This picture shows you how these salinol groups are derivatized chemically to make it hydrophobic. Now the surface hydrophilicity is now getting converted into derivatized silica gel with different groups. Sometimes it is even derivated with the amino group, sometimes it's derived with a phenol group, sometimes with a C18, C4, a C8, C4, C12 or C18, C30. All these things are derivatized on the surface to give interface for different sort of polarity for separating nonpolar compounds. When you just try to compare the column along with its polarity, this picture explains you how they are equivalent. When you have a normal phase silica column, which is hydrophilic in nature, which is equivalent to water, but C18, if it goes to the extreme corner, C18 which is hydrophobic column, and for which it is equivalent, the polarity is equivalent to that of hexane. Therefore, crisscrossing them. For silica, we use hexane as a mobile phase. For C18, we use water as a mobile phase. So intermediate solvents like methanol or that side benzene are mixed together to get a variation in the polarity, to get a smoother separation, either by using adsorption or by partition principle. Let me just tell you a thumb rule which is used while choosing the type of columns. In case of the compound, based upon the type of compound, we choose the stationary phase, especially the chemistry of the stationary phase. If it is a neutral compound or if it is acidic or basic, reverse phase is best. So the crux, the important indication or important use of using reverse phase is you will be using water-based mobile phases in which you will be able to play around with either pick reagents or by using pH modifiers. It is a thumb rule that you know about the pKa of the compound. That is, if you know the pKa, either you go this side or that side of pKa, you will be able to get the compound unionized. That unionized compounds are more hydrophobic. Therefore, you try to adjust the mobile phase in such a way, the pH of the mobile phase, so that you are little above or below the pKa of the compound. Thereby, you make the compound unionized. The unionized compound stays more time in C18 column. So, by using this principle, you will be able to make the compound to stay for more time to get it separated over the period of time. So, typically mobile phase used here are water or organic modifiers. The second type is ionics, basic and acids. When it comes to this kind of compounds, you may prefer to have an ion pairing reagent. But sometimes it's very difficult to elute some type of compounds. So especially simple aliphatic compounds are very difficult to elute by C18 column. Therefore, ion pairing agents are used. These ion pairing agents make some sort of a bonding with this analyte, and that helps it to make it hydrophobic temporarily in the column. Thereby, it can be eluted either by C8 or C18. Again, water along with the pick reagents are used, that are typically ion pairing reagents. The compound, if it is not soluble in water, then you have to use a normal phase, then in which silica, amino or cyano or diol columns can be used along with organic solvents. Here we can't be able to use water-based solvents. Or ionics, inorganic ions. Sometimes when you go for inorganic ion analysis, in that case ion exchange mode has to be used, ion exchange columns where aqueous buffers and counterions are used. Here exotic conditions are used to do the elution. Sometimes the pH, you won't be able to see that pH in reverse phase. Those pH ranges are used for this separation. In case the compound is having higher molecular weights or polymers, you have no choice except to use size exclusion chromatography, like polystyrene silica, or using mobile phase gel filtration, especially aqueous gel filtration reagents can be used. The chemistry based separation preferences, when you just look into the array of things what you have, in the polar solvents you have acidic, neutral and basic. If it is acidic, you have to go in the acidic pH, especially to make it unionized. Therefore, you can go for ion exchange or polar exchange, not like graphite, or anion exchange, or reverse phase mixed mode can be used. Or if it is neutral, non-polar, mild polar or highly polar compounds, highly polar solvents, especially reverse phase, polar retention or a helic column can be used. If it is neutral, polar solvents when we are trying to use it. Our basic compounds, you have to go for alkaline pH to make it unionized so that it can be eluted out. Here you have to use cation ion exchange or polar retention or RP, chromatography. These kind of things can be used for a basic compounds. But basically that most of the column you should be careful about the range in which column could work upon. Safely that most of the columns work between 3 to 7, all the reverse phase chromatographic columns, but going beyond 7 or less than that of 3, you will definitely damaging the column. Thereby you have to work into the column chemistry which is suitable for getting into this kind of pH. Basically, otherwise silanol hydrolysis is unpredictable. The whole the bed will be disturbed by that way. So non-polar solvents are used for normal phases only, where all polar solvents are used for both all acidic, neutral and basic molecules by using different type of pH range and different type of columns. Enough amount of preference to work with polar solvents. This typically when you look at the HPLC chromatogram, all of you know about you get peaks. But the peak is, so for example, one side you have absorbance, another scale in the x-axis scale you have time in minutes. Now the most important thing is that how much resolution you are getting it for peak A and peak B. Peak in HPLC, as far as HPLC is concerned, the peaks has to be clearly isolated from each other. The method optimization or method validation, everything is coming only after understanding the peak separation is reached very well, and it fits into the qualities of a fine start and a fine end of a peak. So the one which is the faster moving compound is less retained in the column than the slower moving is more retained. Basically, if it has more affinity towards the column, it goes slow, as I told you before. Usually the peak area is quantified by a simple mathematical equation based into height by 2, but but this is a pretty old method, but we use by different type of parameter we try to scale the area of peak, or sometimes we even use the peak height to quantify the amount of substance. Now at various concentration the standards are injected into HPLC and graded series. So the standard response what you are getting and the multiplying response what you are getting as a peak height increase or a peak area increase is noted down. With that, calibration curve is plotted, and using that calibration curve the unknown concentration is determined by a mathematical calculation. A typical chromatogram what you see here, you need to understand few terminologies. Sometimes what we call it as a void volume. Void volume is a empty volume which is not having any peak. Basically this shows how much volume of solvent is in between the injector as well as the column, as well as the detector. So first, this whole amount of solvent we represent as volume 0. Any compound which is emerging out, which is not retained in the column, will be emerging at VO, that is V0, it will be coming out, so which is not retained at all. So after that the separation start taking place. So understanding the void volume is very important while determining a capacity factor or a separation factor. A capacity factor is something that how good your peak is getting separated from the void volume. That is very important. By using this very simple equations we try to determine that. The separation factor is another dimension which shows between two peaks how good the resolution you are getting it. That is what is explained by a separation factor. When you are trying to run typically an HPLC, in which suppose if you are running with 1:1 methanol water, when you just try to inject a compound like you inject a pure acetonitrile, and you will be getting a notch. That notch shows that some sort of a negative deflection. It shows that first the compound is coming out which is not retained in the column, so you see that is a V0, that is a void volume in which you are not expecting anything which is retained is coming out. I have explained you already about the columns, column chemistries, about the peak illusions, about the void volume, etc. Now when I come to the detection technique used in HPLC, typically it depends upon the compound, the character of the compound, or the choice of the choice of detector is purely depend upon the capability or character of the compound which is of interest. If a compound is capable of absorbing ultraviolet radiation, so ultraviolet light, then it is detected in the UV. Or if it is a colored compound which the color can be used to detect it, you might prefer to use a visible wavelength. Ultraviolet is for compound which is colorless and having a high molar extension coefficient, you will be able to do by UV. Mostly UV detectors are quite sensitive to detect most of the compounds, but the compound doesn't have any absorbance, you have to look for other property. Photodiode array is another detector which is an extension of a UV detector. In a UV detector, typically you will be measuring a particular wavelength continuously, but a photodiode array detector in which continuously you will be detecting all nanometers over the period of time. A differential refractometer is the detector through which you try to quantify the changes in refractiveness of the medium. It is suitable for sugars and substances which are having the capability to change the refractive index is monitored. It is a pretty non-specific detector to work with. Next is fluorimetric detector, where a fluorescence is employed here. Fluorescence spectroscopy is one of the very sensitive technique, very accurate, and you can reach literally, you can exceed UV detector capabilities. But only problem is all the compounds are not fluorescing. So the compounds which are capable of fluorescing can be detected by this way. Next is the electrochemical detector. Electrochemical detector is one of the widely employed detector for the detection of neurotransmitter once upon a time. The electrochemical detector works based on the basic fundamental of redox potential of a compound. So it's amperometric or colorimetric detection can be achieved by electrochemical detectors. Next comes mass detectors. Mass detectors are pretty sensitive, pretty accurate, and different modes are capable of fingerprinting a compound to the highest accuracy possible. Next comes evaporative light scattering detector. This is again a non-specific detector used for compounds which are not having any specific properties, especially plant extracts can be used to, the ELSD can be used to detect plant extracts where we get a non-specific peaks without any proper character. It just, a light scattering is the principle which is employed here. What you see here is the schematic representation of a UV detector, in which I just try to simplify this diagram, where we have two lamps, either a tungsten lamp gives a wavelength between 380 to 750 nanometers, where deuterium gives UV that is from 190 to 400 nanometers. Deuterium gives continuum. So these lights are switched on and off, depends upon necessity, and where we have a grating which is helping us to determine, or we try to separate a particular nanometer which is of our interest and which is used to isolate a particular wavelength, and it is been fed to a sample, where the sample cell in which continuous flow of mobile phase is happening, and after it is the emerging ray is allowed to fall on a photodiode or a photomultiplier, where it is coupled with an output device to get the continuous monitoring of what is coming up in the elute from mobile phase, from the column. And continuously when you are monitoring, when the compound comes up, you started getting the signal. This slide shows you how a Zerny-Turner monochromator works. It's a grating which is on the surface of this Zerny-Turner grating monochromator, in which light is allowed to fall on them, and it splits into WebGR, and a slit allows a particular wavelength. When you just try to move the grating, then you will be able to separate a particular wavelength to go out through the split. And this is used in older versions of this kind of detectors. We used nickel prism, but this is largely replaced by this Zerny-Turner monochromators. It is something similar to that of, if you just look at your compact disc, that is CD, if you just angle it towards the light, you will be able to see WebGR coming out. Using the same principle, this is also working. Now let us see that how this photodiode array detector is much different from the UV detector. Now here the light is allowed to pass through empty cell which is containing the mobile phase continuously running on, and it is allowed to refract to different wavelengths by the grating, and the different wavelengths are allowed to fall an array of photodiodes. So each and every photodiode is having a particular wavelength to deal with. Therefore continuously one will be able to monitor different absorption of compounds in different nanometers. So here you get a three-dimensional view of the data, and this data can be in one single run you'll be able to understand more than one compounds having a different molar extinction coefficient at different wavelengths. All these things can be observed. It's something, it is a next version of ultraviolet detection with multiple wavelength can be done simultaneously. Factors affecting the efficiency of separation in HPLC. See, there are many parameters which need to be optimized while considering or while we trying to improve the efficiency of separation in HPLC, especially flow rate. Sometimes that we wanted a quick separation, therefore we try to increase the flow rate, but the flow rate can modulate a peak shape. When you go in a slower flow rate, the peak might get widened, or if you go in a higher flow rate, you might get a high back pressure and shutdown, or the peaks are not resolved well. So appropriate linear velocity is required for high efficient separation of compounds by HPLC. Second one is column length. Although that increasing in column length can increase the separation factor between two peaks, but it eats away the sensitivity of that system, sensitivity of that particular method, because when you go increasing the length of the column, the peak broadening is unavoidable. When the peak broaden happens, then you will be losing the sensitivity of the method. Next is about particle size. The particle size of silica beads or modified silica beads inside the column, it matters a lot when it comes to efficiency. When you go lower particle size, the surface area increases more, so the plates increases more, so therefore you'll get a very accurate separation, a beautiful separation. However, it also increases disproportionately, it increases the back pressure, where if I just compare 1.5 micrometer particles with the 10 micron particles, there would be a pressure difference of 800 pounds per square inch to 15,000 pounds per square inch. Therefore, a Van-Ditmer equation explains this kind of problem in analytical separations. Therefore, you need to choose the column which is of your interest, considering the type of machine what you are trying to use it on. Next is about distribution of particle size. The uniform particle size, if they are, you get much more better peak shape. If it is not, you might set FSR as 1. Column bed packing. The bed packing is another important parameter, but however, if you now today, we never go for packing the column, as commercially available columns are packed very well, so these kind of problems are not much encountered right now. Porosity of the packing. Sometimes people try to drop the column on the floor from a height of 1 meter or 1.5 meters from the bench, working bench, which can disturb the pack, and it can cause porosity, it can cause cracks in the column. It can cause voids. These voids will be causing these voids will cause malfunctioning of the column, especially when you get a separation. The porosity is very important. That is also governed by the size of molecule you're trying to work with. Sometimes for protein you look for 300 amp strong pore size, because the proteins are big in molecular size. So the pore size is very important for a type of molecule what you're trying to work with. But at any case, the porosity increases in case if the bed is disturbed, then it is called as a void column. Volume of injection. The volume of injection is another parameter. You try to keep it as small as possible. If you try to increase the volume of injection, you might get disturbances in the sensitivity of your compound. And the type of solvent which is used, that is the last point, the strength of the injection solvent can also vary the separation which is caused. The temperature, viscosity, and the tubing length, all these parameters can differ or it can alter the efficiency of the separation by HPLC. Especially when you are working with solvents of having high methanol concentration, you would get higher viscosity, thereby you get high back pressure as compared to the same proportion when you with acetonitrile and water. So students, let me summarize what we have seen or what we have learned from this today's module. We have seen about the basic construction of HPLC and various parts of HPLC and about their functions, columns used in chromatography, and the separation science behind it, and their types too. We have seen about typical HPLC chromatogram and detection methods being employed in HPLC for getting the signal about the presence of a compound. Thank you.